Okay, this is the second part of a four-part video addressing a tutorial from financial maths. It's about the call option, Black-Scholes call option pricing model. But part of it, of the tutorial, we are asked to prove that this is equals to this. As I mentioned in the previous tutorial, part one, this is the strike price, this is the interest rate, this is the time to maturity, this is the probability distribution function of the and then this is the probability distribution function also, and this is the current price of the share. So this notice different from there's a difference you from, although this looks like very similar to the thing here. Okay, it's very look similar to the thing here, and this thing here looks very similar to this thing here, but they are not the same. There's one major difference is that there is no, you see this thing here, this prime, and this what you call the prime here. It means that there's no prime over at here. That means this means that this is after this normal, this is cumulative differential cumulative distribution function has been differentiated and to arrive at the probability distribution function. So m prime x we call the normal PDF, or the normal distribution probability distribution function, but this is the cumulative distribution function CDF. So there's a difference. If you want to know more, you can Google cumulative distribution function and probability distribution function of a normal distribution function. Normal here doesn't mean the normal, it's a specific type of not distribution, probability distribution. So now I'm going to prove this. So I'm going to prove from the right hand side to the left hand side. That means here I'm going to prove from here to arrive at here to show that they are equal and answer the question from the tutorial. So first thing, okay, okay, let me get some power source. So the first thing that I'm going to do is ke minus r, that means the right hand side of here. I'm going to change it. Let me get some power first. Okay, hope it works. No, there's not enough power. Okay, okay, and it's getting, yeah, should be getting enough power now. Okay, so then we will, okay, so for this part, ke minus rt m prime d2. Okay, I'm going to show this. So using number 3, so I'm using 3, so this is the call option pricing formula. So the d2 comes from here, d2. Okay, so this d2, using this formula given, this definition of d2, I change it to d1 minus sigma root t. I change this d2 to d1 minus sigma root t. Alright, I've changed nothing else except that from coming from here to here. So, and then using number 4, this number 4, okay, this is the probability distribution function formula. So you can Google for it, you'll find that this is the normal probability distribution function formula. So that means when I change my x, right, if in the function, if I replace this x by 3, this x has to be replaced by 3. If I change this to 4, then this x has to replace by 4. That is essentially what it means by a function. So then in this case, because my x has been changed to d1 minus sigma root t, so therefore the x here has to be changed to d1 minus sigma root t, and we square it, and everything else would be the same. Root 2 pi, this one is root 2 pi, e we have it here, 2 we have it here, so minus we have it here. So it's exactly the same, except that the x has been replaced by d1 minus sigma root t, and there we have this ke minus rt, where I'm not changing anything. So now using 5, number 5, which is this, the quadratic expansion formula for the top part. Okay, because this is a bracket square, same thing like this. Now my a is my d1 and my b is my sigma root t. So when I do this expansion, d1 square is my a square, minus 2 times a is my 2 times d1 and sigma root t. So you just match to this. So b square, that means the square of this second term here. The square of this term here will give me sigma square t. Okay. If you are not familiar with indices, this is the rule for the indices. This is how I arrive at from sigma root t square, how the square of sigma root t, how I get sigma square t came from these two formula. So you're going to have a look. So then in detail, you can pause any point, you can pause the video to have a detailed look at this and match it with the figures here, so that you know exactly how I derive from step to step. So then here we have to come from this step to this step, I use equation 6 and 7. So since this is basic algebra and I shall not deal into the detail, so this one I'm just basically getting this e minus d1 square out of it. Using algebra, I get it out, so root 2 pi. And the reason I want to get this out, right, is this is exactly my m prime d1. Okay, you compare with this thing here, m prime d1 is just x replaced by d1, I'll get e minus d1 square over 2, isn't it? And that's just this here. So I'll get it out so that I can change it to this. I'll get one step closer to the formula here. And e, this one, those after getting out minus d1 square, I'm still left with the minus 2d1, minus minus become minus times minus become plus, and the 2 cancel away with the 2 here. The 2 cancel away with the 2 because divided by 2, so there's no more 2 here, so left with d1 sigma root t, and minus, okay, this thing need to divide by 2, okay, and then minus multiply in, so you get minus here, so you get minus sigma square t over 2. That's how I arrive to this step. Then the third step, I make using 4 and 2, that means using this equation, over here, I change this part to this part. This is using 4, and using 2, okay, this one I change the I didn't change anything else actually. In fact, I only changed this. So I'm going to, from here, I'm going to move on to the next page to continue with this formula. So you see that this part is exactly the same as the one in the previous page. We have m prime d1. You see we have m prime d1. We have k minus ert, ke minus rt, ke to power minus rt, and then we have this d1 sigma root t minus sigma square t over 2, so which is the thing here. So it's exactly the same. I'm just copying over to the other page. So now we have m prime d1. I need to prove that I already have this over here. I just need to prove that the rest of this is the same as this one. So the trick is using 7, I mean equation 7 from the earlier. Okay, what is equation 7? Let's take a look. Equation 7 is this. Okay, so just basically just e, that means this e plus this is equals to e of this times the e of this, but e of this multiplied to e of this, that's why you get the rt minus rt over here is in this law or power rules. Okay, so then the k, I'll just move over to his side because a multiplied to b is the same as b multiplied to a is the same. So k is multiple is commutative, so I bring the k over in front, and doesn't matter much. So e ln we just know that, okay, e ln x equals to x. This is log rules, right? So we just then the x we just bring down. So x in this case is like my s naught over k. So s naught over k, bring e ln would disappear. Ln and e or e ln would disappear. So it's the same. Okay, so this is another rule, same rule for log rules. So they are the e and the log are or log base e. We prefer to call it log base e. They are the inverse of each other. The exponential and the log base e are inverse of each other. So when they are together, they cancel off and leave you back with the original x. And so here then we have this thing would become row it will become this. So this would simplify to this part. Okay, this part will simplify to this part, and rt minus rt is 0, right? And then e to the power of 0 is just 1, and so k would cancel with k, so I'm left with s naught. So we result in s naught m prime d1. So that would be the I have proof for the 1a. That would be the second part of this video. So for the rest of the video, again, you can visit to see the other parts of the video. If you cannot find, just give me an email. .com. Okay, that's it. I'll proceed to the third part. To prove, I'll end the video here. I'll proceed to the third part in another video. Okay.